Okay, so thank you. So I'd like to begin by just carrying on a little from where we left off this morning. And so the last thing we were discussing this morning was the question of ionization of disks. And in particular, we were talking about thermal ionization of disks. And we were saying that if we had temperatures above about 1,000 degrees Kelvin, then we would expect the alkali metals to be ionized. And that ionization would perhaps be enough to enable the gas to couple to the magnetic field. Now, what about if we have temperatures below 1,000 Kelvin, which are going to be the temperatures that are going to be present in most of the protoplanetary disk? Well, in that case, we're in the regime instead of non-thermal ionization. And so non-thermal ionization in general is much more difficult to treat than thermal ionization, because when we think about non-thermal ionization, we really have to explicitly consider the processes that are ionizing the gas, and then the recombination processes which will remove ionization from the gas and return it to being neutral. So we need to know the explicit ionization rates, so that will generally be ionization from various kinds of high-energy photons. We'll say more about that in a minute. And then we need to know the specific reactions that lead to recombination. And individually, these things are not too bad. So, for example, if the dominant reaction is so-called dissociative recombinations, this would be a reaction of this kind. You take an electron and a molecular ion, here it's HCO+. These recombine, and in the process, the HCO+ is dissociated into H and CO. So if you have a reaction of this kind, you can write a rate equation. So this would be the time dependence of the electron number density. And so this would have two terms, one reflecting the rate at which neutral species are ionized, and then a second term, a loss term, reflecting the rate of collisions between electrons and HCO+ ions, which will lead to recombination. And this will involve some rate coefficient, which hopefully someone has measured or calculated with some accuracy to enable you to determine how fast this recombination reaction will proceed. We then say that we're in ionization equilibrium, so this equals 0, the time derivative equals 0, and then if we assume charge neutrality for this particular reaction, so that the electron number density and the ion number density are the same, we can just straightforwardly solve for what the electron abundance will be in terms of the ionization rate and this rate coefficient, which will generally be some hopefully known function of temperature. So for an individual reaction, this kind of thing is quite straightforward. The problem, of course, arises from the fact that in principle there may be many such reactions that are important in the disk, and it may be quite difficult to determine a small subset of those reactions which give us a reasonable approximation to the overall scheme of chemistry in the disk. Now, of course, the central question here is, what are the ionizing sources? And here there's really a competition between different ionizing sources which have varying degrees of intensity and various degrees of penetrating power through the disk. And so here are maybe 3 or 4 of the most important ones. So if we imagine this would be the surface of the disk and the ionization is coming from external sources, the most penetrating radiation that might be present is cosmic rays. And it's not at all clear whether cosmic rays actually make it to the region of the protoplanetary disk or are instead screened by the protostellar wind, which may prevent cosmic rays in the interstellar medium reaching the disk. But if they do reach the disk, those particles can be quite energetic, and so they may have a stopping depth, an exponential attenuation length of order about 100 grams per square centimeter of column. So those will actually penetrate a reasonable distance through the disk before they're absorbed and give up their energy in the form of ionization. Now, in addition to cosmic rays, we definitely have stellar X-rays, and the more energetic of those, say at around 5 keV, those may have a stopping depth of several grams per square centimeter. So those can be quite intense sources of radiation, but compared to the cosmic rays, they have maybe an order of magnitude less penetrating power through the column of the disk. And then finally, we have far ultraviolet photons, which are very numerous, and those will be able to ionize species such as carbon and sulfur. And once those species are ionized, we may actually get quite a significant degree of ionization, maybe 10 to the minus 5 or thereabouts. But those species will really not make it very far through the disk at all, maybe 1/10 of a gram per square centimeter or even less than that. So those will really be just ionizing a very thin surface skin on the top and bottom of the disk surface. So those are all external ionization sources. We also potentially have radioactive decays, as was being discussed this morning. Aluminum-26 is normally one of the dominant species there, and that material will presumably be incorporated in dust grains that are either throughout the disk or perhaps have sedimented towards the midplane. So those will be providing ionization sources really in the body of the disk, whereas the external sources will be ionizing from the top and the bottom. So we can consider those different sources, and here's a schematic of this based on a rather simplified model developed by Neil Turner and Sano in 2008. So this is ionization rate on a log scale as a function of the column down from the surface of the disk down towards the interior. And here are just some representative curves for stellar X-rays, for cosmic rays, and for radioactive decay, making various, hopefully reasonable assumptions about the intensity of those ionizing sources and where we are in the disk. And the point simply is that if we're at 1 AU and we think the surface density, the column, is of order 1,000 grams per square centimeter, or perhaps even higher than that, all of these external sources, even the cosmic rays, will be very, very strongly attenuated by the time we reach the midplane of the disk. And what we'll have left is just the radioactive decay, which is at really a very low level of ionization compared to these external sources near the surface of the disk. So the general picture, the qualitative picture we then have, is that the surfaces of the disk may be reasonably well ionized, but that if we're really interested in the midplane, in sort of the terrestrial planet-forming region, at 1 AU, 2 AU, a few AU, that region is both very cold, so the thermal ionization will not be effective in giving us a decent degree of ionization, and it's also very dense and therefore shielded from the most important external sources of ionization. So this region will have a very low ionization fraction, and as we'll argue tomorrow, that probably means that it doesn't interact strongly with magnetic fields in that region of the disk. So we'll go on and discuss more about the consequences of that low ionization fraction tomorrow. But for today, I want to now go on and consider some questions of disk evolution. And the two topics I really want to cover today are, first of all, to go over the classical theory of disk evolution, and then also to say something about the limitations of that theory. How applicable is it, and should we be using it, given that we perhaps know that really how angular momentum is transported in disks is quite a complicated topic. So let's begin with the basic problem here, which is not just in protoplanetary disks, but also present in other accretion disks. If we have a gas disk that is orbiting a point mass, the orbital velocity there is quite accurately Keplerian. And so we argued this morning that the orbital velocity of the gas is the Keplerian velocity, and the correction term is only second order in h over r squared. So if we consider the specific angular momentum of the gas, that would just be gm star r, and that's proportional to r to the 1/2, and it's an increasing function of distance from the star. So we have here a sort of a tension between what the disk would energetically like to do, which is to accrete onto the star. If the disk at large radii accretes onto the star, it gives up gravitational potential energy, so there's energy liberated, free energy liberated during that accretion process. But that tendency for things to accrete on energetic grounds is competed against by angular momentum, which, if nothing else happens, actually forbids that material being accreted. Gas at large distances in orbit around the star has too much angular momentum to be accreted, and so it would just want to sit there in ordinary Keplerian orbits. So this is the central problem, and of course, some sense this is why disks exist in the first place. We already said that disks are very long-lived structures living for millions of dynamical times, and that is reflecting the fact that basically they're very close to being stable equilibrium structures of gas around a star, which actually only want to evolve on really much longer timescales than the dynamical timescale. So how can we allow angular momentum to be either lost or redistributed in order to be accreted? And for a long time, there's basically been two separate models for how that might happen. So the first model is one which treats the disk itself as being basically an isolated object, and all the action we're interested in takes place within the disk gas itself. And the picture here is that the disk gas is turbulent, so you might imagine it has turbulent eddies in it, which mix material at different radii from the star, and that mixing process leads to the angular momentum being transported outwards in the disk, and then as angular momentum is transported outwards, gas in turn can flow inwards to be accreted. So this is described as a viscous disk because it's the same kind of evolution you would have if the fluid was very viscous, if it was like honey or something like that, and so there were shear stresses within that disk, which again would transport angular momentum. However, there's a second possibility, which is connection, basically, of the disk with the external environment. And the specific example where this can happen is if the disk is threaded by a magnetic field. So imagine here's the disk, and now this is a magnetic field line which penetrates the disk and then extends off to infinity at some large radius. And the basic picture here is that you can imagine magnetic fields, if they're strong enough, to be somewhat like rigid wires. So if we took some gas and moved it away from the disk in a wind, it would follow this magnetic field line, and it would be like following a rigid wire which was anchored to the surface of the disk. So as that gas parcel moved further away from the disk, it would actually spin up, it would gain angular momentum, and that gain of angular momentum would have to be compensated by a loss of angular momentum from the disk, which would be mediated by a magnetic torque on the disk surface. And so if this field line behaves in this rigid way for sufficiently large distance away from the disk surface, a rather small amount of material flowing out along this magnetic field line can remove a lot of the angular momentum from the system, causing the gas that's remaining in the disk to flow vigorously inwards towards the star. Okay. So these two are often sort of considered to be separate hypotheses, viscous transport versus wind transport. But one of the things I'd like to emphasize, and we'll say more about tomorrow, is that really these are not mutually exclusive. It may well be that the processes which lead to, if you like, viscous transport also give rise to disk winds, and there's some mixture of angular momentum transport and angular momentum loss, which both contribute to the gas in the disk being able to accrete onto the star. Okay, but let's first of all think about this viscous transport question. And the simple way to think about this dates back to work by Lindenbell and Pringle and Shakur and Sunyaev way back in the early 70s. And the approximations they made were to consider disks that were geometrically thin, which we've already said protoplanetary disks satisfy that condition, that are axisymmetric and planar. So the simplest sort of model disks you could imagine. And they considered angular momentum transport within the disk that could be modeled as if it was a Navier-Stokes viscosity that would be appropriate for an ordinary terrestrial viscous fluid of the kind that's studied in terrestrial fluid dynamics. And the critical quantity there is the kinematic viscosity, which we label as nu. Now, the key point here is that although this sounds like a complicated thing, a Navier-Stokes viscosity, and so on and so forth, actually there's really only very simple considerations that are needed in this case where we're considering an axisymmetric planar disk. So the basic equations that are being dealt with are two. One is the equation of mass continuity. So sigma here is the surface density. VR is the radial velocity. So we have one equation just reflecting the fact that in this model there are no winds, and so mass has to be conserved within the disk as it flows in. It's neither gained nor lost during that process. And likewise, angular momentum is conserved. So this is basically the same equation for angular momentum, where we've multiplied this surface density here by the specific angular momentum, r squared omega. So it's the same conservation equation on the left-hand side, but now we've allowed on the right-hand side an evolution term, which is our torque, reflecting the fact that different annuli in the disk are rotating at different speeds. There's some shear between those different annuli, and therefore if this is a viscous fluid, there will be a viscous torque between those two annuli, which will enable them to share their angular momentum. And the key assumption of these theories is that this torque G is a local torque, so it's described just by the local conditions in the disk, and it scales linearly with the shear. So it involves this term d omega by dr, where omega is just the Keplerian angular velocity. So this term here just has a simple interpretation. Nu sigma r d omega by dr is the viscous torque per unit length. 2 pi r is the circumference of a circle, and then we multiply by another factor of r in order to get the torque, the lever arm for the torque. Okay, so you can take those two equations plus the specification for the torque, and if you assume that the potential is Keplerian, you end up with an evolution equation for the surface density in the disk, how the surface density in the disk would evolve with time given this viscous stress, which is redistributing angular momentum. And this is the form you get. It's a rather simple partial differential equation, which has the form of a diffusion equation. You see on the right-hand side here, it involves two spatial derivatives of the radius. So it's of the same form as an equation describing heat diffusion in a metal bar, or one of those classic examples of diffusion that one encounters in physics. And the key timescale here we describe as the viscous timescale, and it's the square of the scale we're interested in divided by the viscosity. So if we know something about the viscosity, and we know something, say, about the scale of the disk, the viscous timescale to order of magnitude will be the timescale on which this viscous redistribution of angular momentum will lead to a significant change in the surface density. And this equation has simple solutions in some limiting cases. If we assume that the viscosity is a constant, then there's a Green's function solution which describes how a ring of material initially placed in orbit around the star would spread out and diffuse under the action of this diffusion equation. So here's what the initial condition would be. It would be just a spike at this radius, and then these curves here show how that material spreads out and accretes onto the star. And the property of the solution is that, given enough time, the mass all flows towards the origin. It all flows towards r equals 0, towards where the star would be in a more physical system, while the angular momentum, which has to remain conserved, moves further and further away from the star, and so is effectively carried out by a tail of the material, which just keeps on moving further and further away. So given enough time, all of the material effectively accretes, all of the angular momentum remains in the system, but it remains in a vanishing amount of the material that has moved out to very large radii. Okay, so that's a time-dependent solution. There are then some other solutions which can also be derived from those same kind of equations. One is a steady-state solution if the viscosity is a power law in the radius, so it's r to gamma, where gamma is some power. Then in a steady state, the surface density away from the boundaries is just the accretion rate divided by 3 pi times that viscosity. So it's then inversely proportional to this power of gamma. There's then also a self-similar solution, which may be more interesting or useful for actually modeling observations, which describes what happens if you have a power law, which is given by this kind of steady-state solution, which is then truncated, essentially something like exponentially at large distances. So if you have a system that is initially that kind of power law with a cutoff at large radius, there's a self-similar solution that describes how that evolves with time. And here it is plotted graphically. This would be the initial condition with a relatively compact disk going out only to 10 in these units. And then as time progresses, the surface density in the inner parts drops, but the size of the disk increases, and this cutoff gets pushed out to larger radii in the disk. So I've given the explicit form for this solution here. Obviously, that doesn't matter here. The one thing I'd like to emphasize is that if you have a very simple disk model, say, where the surface density goes as r to the minus 1, which is not an unreasonable number to have, then this solution describes an r to the minus 1 power law at small radius, and then actually just a simple exponential cutoff beyond some radius within the disk. So you often see that solution, or sometimes see that solution, used for modeling observations, because this is a solution that has a rather small number of free parameters that in principle you could constrain with actual observations of the surface density profile in disks. And that's quite a good model to be considering, because as you can see, it follows quite straightforwardly from just basically mass and angular momentum conservation within the disk. Okay, so those are sort of classical models for the evolution of viscous disks. Now, I think a more important point, and maybe a more subtle point to discuss, is how applicable that sort of simple theory is to what's really going on in protoplanetary disks. And the issue here arises because these equations from which this theory is derived, the Navier-Stokes equations, apply to viscous fluids, where the viscosity strictly is coming from molecular processes within the fluid. The sharing of momentum and angular momentum by random motion of molecules within the fluid. And if we actually ask, well, how large that kind of viscosity, that molecular viscosity would be in disks, the answer is that it's very small. So here's the simple calculation. The molecular viscosity would be something like the sound speed times the mean free path. We said before the sound speed was something like kilometers per second. The mean free path might be centimeters or tens of centimeters, depending on where we are in the disk. So if we multiply those numbers together, we get a viscosity that's about 10 to the 6 in CGS units. If we then estimate the viscous timescale, r squared over nu, for some reasonable scale in the disk, let's say 5 AU, the viscous timescale we get is something like 10 to the 14 years. So even for a theorist and even to astronomical precision, this is a failure of the theory, right? We want the disk to evolve on a million-year timescale, and here we are 8 orders of magnitude longer than that. So if there was nothing else going on in the disk apart from really the true viscosity of the gas, there would be no reason for the disk to evolve at all, and all the stars that had ever formed in the universe would still have their disks surrounding them, and nothing would have happened there. So ordinary viscosity, the kinematic viscosity of Navier-Stokes theory, has really no role to play in disks except on very, very small scales, which may be relevant and interesting for things like particle concentration, but not for the overall evolution of the disk. However, an important result is that the same basic evolution equations will apply, providing that there is some other process, normally considered to be some turbulent process, which redistributes angular momentum. And the basic constraints on the turbulence that we need in order for that mapping to hold is primarily just that the turbulence is locally defined, so that the amount of angular momentum transport just depends on the local properties of the disk and doesn't depend in some more complicated way on the global properties of the disk far away from the region that we're considering. So in particular, if we have a stress within the fluid which is given by fluid stresses, so these would be perturbations to the radial and azimuthal velocity, these would be magnetic fields in the radial and azimuthal direction. If these are fluctuating quantities, characteristic of turbulence, and we average over space and time to determine an average stress there, we can basically use that same mathematical formalism and get out the same overall evolution equation. So we would still expect in that case, as long as we ignore very short timescale fluctuations that would be due to the turbulence themselves, we would still expect the disk basically to evolve in the same way over long periods. Okay. So this is a very useful way of thinking about things, because it means we don't have to worry necessarily about the true viscosity within the disk. We can have turbulence, and broadly speaking, the disk will still be expected to behave in the same way. Okay, so that's a good thing, and if we are only interested in the one-dimensional evolution of the disk, so the surface density, how that evolves in radius and time, we really have a reasonably solid foundation to be using that kind of classical theory to describe the disk evolution. However, there are plenty of places where this kind of analysis can go wrong. One, of course, will be if we have a transport mechanism that is intrinsically non-local, which will, of course, violate then that locality assumption. And the one case where that may happen in practice is self-gravity. And it turns out that if self-gravity operates in a disk that's relatively thin, it can often be described as a local process. But if we have a very massive disk, say a disk that is the same mass as the central star, then that disk will, for example, be unstable to developing bars, be more like a galaxy-type model, and that will definitely be a non-local transport process that cannot be described in that kind of simplified one-dimensional way. Obviously, if we have things like mass loss, we have to worry about that. We also have to worry about one-dimensional situations if omega is a long way from Keplerian. I'll mention one of those in a minute. Obviously, if we think about very short timescale phenomena, then the properties of the turbulence may be the dominant thing we're seeing rather than the long timescale evolution of the disk. And then finally, most importantly perhaps, we have to be very careful if we go away from one-dimensional situations to two- or three-dimensional situations if we continue to use the same equations that are derived from Navier-Stokes viscosity. So if we start thinking, for example, about eccentric disks or warped disks or disks that have some unusual configuration, quite often we find how those disks evolve will depend explicitly on what the angular momentum transport within the disk is doing, and it may be very different from the predictions we would get from a Navier-Stokes model. So we can use the classical theory in some limits quite securely, but whenever we do so, we have to keep in mind that the viscosity is not really a true viscosity, and if we push too far into the wrong directions of parameter space, we might end up with actually a qualitatively incorrect answer for how the disk will behave. Okay, so that's one approach. That's the sort of simplest approach, where really all we've done is to take mass and angular momentum conservation and use fairly general assumptions that say that angular momentum is redistributed by some sort of viscous or turbulent process within the fluid. Now, the next thing we can do is to try to be a bit more ambitious and really try to specify how the viscosity depends on some local quantities within the disk. And in principle, there's many things we could do here, but by far the most famous and the most used in astrophysics is the so-called alpha prescription. So the idea here is that we take this viscosity and we write it as the product of the sound speed and the disk scale height multiplied by a dimensionless parameter alpha. And if you want to, you can motivate this in terms of a sort of turbulent eddy model, where you imagine that there are eddies in the disk which have some scale, which would probably be less than the disk scale height, because if the eddies were larger than that, they would be larger than the largest small scale in the system. And they have some speed, which is something like the sound speed or smaller, because if it was larger than the sound speed, they would be supersonic, and they would lead to shocks and dissipate rapidly. So you can motivate some scaling of that kind, and that would suggest that this alpha parameter here would be less than unity for a model in which turbulence was composed of eddies within the disk. So if you have a model where alpha is additionally assumed to be constant, then you end up with, in fact, effectively a one-parameter description of protoplanetary disk evolution, which can also be used to derive a whole bunch of other properties that you might be interested in. For example, how strongly the turbulence will stir up dust particles, whether it will allow dust particles to form a thin layer in the disk midplane, or whether instead they will remain suspended throughout the disk. So a large number of things you might be interested in observationally can then be pinned to one parameter, and you might hope to try to constrain that parameter from a range of observations and ask whether those constraints are consistent. Now, a simple thing you can do would be to identify the disk lifetime with the viscous time at the outer edge. So if you do that, take the viscous time, which is generally r squared over nu, substitute this formula for nu, and you find that this viscous time is h over r to the minus 2 times 1 over alpha omega. If you take a viscous time of 1,000,000 years at 30 AU, so you say that disks maybe typically have an outer scale where that exponential cutoff would take place at about 30 AU, over 1,000,000 years timescale, there's been significant evolution, such that over several million years timescale, the disk is completely gone. So then we know what the viscous timescale is, we know what h over r is, we just need to solve for alpha, and you get a value there of alpha of about 0.01. So that gives you a sort of a metric of how efficient angular momentum transport is within disks. Measured in terms of this alpha parameter, 10 to the minus 2 is a sort of ballpark figure that needs to be satisfied by whatever physical process you think is creating that viscosity. Now, you can go much further than that. For example, well, first of all, let's just note that if irradiation dominates with a fixed temperature profile, then actually an alpha disk is just equivalent to something like having the viscosity proportional to R. So a fairly general result people get is that if you consider alpha model disks, the equilibrium surface density profile, which remember goes inversely with radius with how the viscosity goes, is something like sigma going like R to the minus 1. Okay? So that would be the sort of steady state surface density profile you would tend to predict from an alpha model. But you can go further, because if you have an alpha model, you could also attempt to construct a model for the vertical structure of the disk, and therefore give an idea for what the disk looks like, not just in the case where it's irradiated externally by the star, but also where the heating is coming from accretional heating as material is flowing towards the star. So here's just an example of that. This is work by Robbins-Bell from 1997. This is the mid-plane temperature as a function of radius. This is this solid black line here. And here what you can see is that the midplane temperature has a fairly complicated spatial dependence, reflecting the fact that as we go closer to the star, we get to higher temperatures, and we start experiencing different regimes of opacity at the temperature of the midplane of the disk. And for this particular model, the snow line at about 150 Kelvin would lie somewhere like at 4 AU. Okay? So this is a model with about 10 to the minus 7 solar masses per year of accretion onto the star. So that would suggest that if we want the snow line to be at about 3 AU in the solar system, we would be thinking about accretion rates that would be a little bit less than 10 to the minus 7 solar masses per year. Okay, so you can make those models, and there are many such models in the literature. But here we need to ask quite carefully, what are the limits of validity of those kind of prescriptions? So the first thing I think I would say is that if we just consider alpha as a mapping between the viscosity and the local properties, the sound speed and the scale height in the disk, of course we can always write the viscosity in this kind of form. So if we imagine that the viscosity was, if you like, an unknown function of the parameters, we could always convert it into alpha being a somewhat different unknown function of the parameters with this scaling with the sound speed and the disk scale height. So that's obviously a sort of trivial relabeling of the problem, going from the viscosity to instead alpha, if we want to imagine alpha as being in some way a more fundamental parameter. However, generally, when we think of alpha theory, we don't think of it in that way. Instead, we think of alpha as being something like a constant. And so, in that terms, alpha is a useful way of describing things if this scaling, with this sort of assumed scaling with the sound speed and the disk scale height, encodes, if you like, the leading order properties of the angular momentum transport in the disk. If, to a first approximation, the viscosity is a constant times the sound speed times the scale height, and then the alpha parameter just varies perhaps slowly with other properties of the disk, then in rewriting things in this way, we've encapsulated the leading order dynamics of the turbulence, and we've actually made progress in developing a predictive theory. So this may be true in many circumstances, and actually in black hole accretion disks, this is probably quite a good way of thinking about the problem. In protoplanetary disks, it's less clear because of the fact that the disk is so cold, and therefore the angular momentum transport processes may be quite complex and may differ from one place in the disk to another. So in particular, alpha is likely a strong function of temperature and surface density if the transport is due to magnetohydrodynamic processes, to MHD processes within the disk. And this comes about because of the fact that the ionization level is low, and therefore the coupling between the magnetic fields and the gas will be very different in the relatively high temperature regions close to the star than it is in the much colder regions much further away. If we're interested in the vertical structure, there are additional uncertainties because the vertical structure, of course, depends on how the accretion energy is distributed vertically. Is it actually mostly distributed near the midplane, where most of the density is, or is it instead a situation where the corona of the disk perhaps has most of the dissipation taking place in a much lower density region? And then finally, of course, if we're interested in comparing against observations, clearly here we've done a very radical compression of potentially very complicated physics into a single number. So that's quite an attractive thing, because clearly we can't hope to constrain a very, very complicated angular momentum transport process with direct observation. So we'd like to simplify the problem as much as possible. But we obviously have to be aware that maybe in some cases we've simplified it too much, and really just treating, say, alpha as a constant throughout the disk is going too far. So I think this is obviously a useful way of thinking about things, but it's one also that we need to be careful about. Okay, so I think let's take a break there, and we will continue in 5 minutes. Okay. Okay, so that's what's going on in the disk. Then the other thing we need to think about is how the disk will interact with the star. So there's a couple of simple cases I want to consider, and then maybe a couple of cases that are a little bit more complicated. So the simplest case to consider is the case which would apply if the star was weakly magnetized, or if for some other reason we could ignore the magnetic field of the star. And in that case, the disk would extend all the way to the stellar surface, and there would be what we describe as a boundary layer, where the fluid in the disk runs into the fluid of the star, and there's some transition in the angular velocity. So in the classical theory, this is very simple. Schematically, this would be what the angular velocity looks like. It's Keplerian in the disk. The star, let's say, is slowly rotating. So by continuity, there has to be a turnover in this angular velocity profile to join the Keplerian disk onto the slowly rotating star. Now, if we have this kind of profile, clearly there's a point in this flow here where d omega by dr is 0, where this is a flat function. So if we go back to those equations that were being used to derive the evolution equation for the disk, the viscous stress, the viscous torque we had there, had this dependence, this linear dependence on d omega by dr. So if we have a boundary layer situation in this classical theory, then at this point, sort of on the outer edge of the boundary layer, the viscous stress vanishes. So we describe this kind of solution as being a so-called zero torque solution for the inner edge of the disk. So the property of a boundary layer is that the star accretes gas with rather high angular momentum. So if this boundary layer is thin, it may or may not be thin, but if it is thin, then this angular velocity, the material that passes through this zero torque radius, has rather high specific angular momentum, and all that angular momentum flows into the star. And then the kinetic energy of the disk, that rotational component to the energy that's been picked up as the material flows inwards, all gets dissipated in this rather narrow boundary layer, which is therefore expected to be rather hot and luminous. Okay, so that's the classical theory of boundary layers. One of the caveats I just mentioned was that if the angular velocity is a long way away from being Keplerian, maybe we need to be careful about using the same formula for angular momentum transport that we use in the Keplerian disk in this very different circumstance. And this is probably true in boundary layers. So when people look at boundary layers in more detail, they find that boundary layer models are very sensitive to the nature of disk angular momentum transport because of the fact that in the boundary layer, the angular velocity is increasing with radius as opposed to decreasing with radius as it does in the Keplerian disk. So fairly recent work by Belyaev, Raffikov, and collaborators suggests that this boundary layer flow is not unstable to magnetohydrodynamic instabilities, but rather is unstable to a different kind of instabilities which give rise to waves within the disk, and that the angular momentum transport within the boundary layer or near the boundary layer is dominated by this wave transport rather than, say, by magnetohydrodynamic processes. So here are some simulations. These dotted lines here show the region of the boundary layer, and here you can see this moderately low M structure of waves being set up in the boundary layer, which sort of slosh around in the boundary layer and move angular momentum from one place to another to allow mass to flow towards that region and join the star. So this would be suggesting perhaps that there's some qualitatively different physics taking place in the boundary layer compared to what's taking place in the disk further away. So this could be important physics. Additional important physics could come from the fact that at least in protostellar disks, the place where we expect to have boundary layers is not probably for vanishingly magnetized stars, which probably don't exist, but rather for stars that have ordinary magnetic fields, but have very, very high accretion rates, such that the magnetic field is overwhelmed and the gas flows all the way down to the stellar surface. So this is what we're talking about tomorrow, the so-called F-Uranus objects, where we have very high accretion rates taking place for a fairly short period of time. So in these boundary layers, the temperature can be very high, and we need to consider how the radiation that's being liberated in the boundary layer is moving outwards through the boundary layer, heating the disk outside, and eventually being radiated into space. So in principle, we need to worry about radiation hydrodynamics, and this was considered by Willie Clay and Doug Lin back in 1996. These are some simulations. Here's the star, here's the disk and the boundary layer, and how that gas is flowing in towards the star. So the boundary layer region in systems where it exists can be quite complicated. The angular momentum transport is different probably from in the disk, and there's extra physics involving radiation, which we may often be able to ignore in the disk, but which we can't ignore in the boundary layer. So there's a lot of open questions here left. Where really is the accretion energy released in these F-Uranus boundary layers? And then perhaps if we went to an analogous situation of circumplanetary disks, so forming planets which are themselves surrounded by disks, perhaps those have boundary layer accretion. How does boundary layer accretion work in that kind of planetary accretion environment? Okay, so that's what we might expect at high accretion rates or weak magnetic fields. If instead we have lower accretion rates or stronger magnetic fields, we expect instead the magnetosphere of the young star to truncate the disk before it reaches the stellar surface. So here's some simulations of that. Here's the star with some magnetic field lines. Here's perhaps what the sort of structure we get. The star here has some closed magnetic field lines close to it. Here's the disk. The disk is threaded by some open field lines, and then as the gas flows in, it's truncated when it reaches this magnetospheric boundary. So we can make some simple estimates of how strong a magnetic field we need for that kind of a geometry to pertain. Let's assume that the vertical field that threads the inner edge of the disk is a dipole. So it falls off as r to the minus 3 with some normalization depending on how strong the magnetization is at the stellar surface. And let's assume that the toroidal component, so as that magnetic field from the star is linking to the disk, the differential rotation of the disk with respect to the star will tend to wind up the magnetic field and give us an azimuthal component as well as the poloidal component which comes from the dipole itself. So let's assume that that toroidal component B phi is of similar magnitude to the dipole component Bz. Then if we ask what the magnetic torque is on the surface of the disk, that will be just the product of those magnetic fields multiplied by the lever arm. And we can then ask what is the time scale for this torque to remove the local angular momentum and therefore cause the gas to flow in towards the star. Okay, so we take the local angular momentum content of the disk, divide it by the torque, and that gives us a time scale on which that magnetic torque would drive inflow. And we can compare that to the viscous timescale to ask when this magnetic torque will dominate over the internal redistribution of angular momentum within the disk. And that gives us an estimate for this magnetospheric radius that depends on the stellar field strength and on the mass accretion rate, and it only involves those parameters to this relatively weak power. Okay, so here it is. This, I should say, is a very rough calculation. There's many ways you can do this calculation. You'll get basically the same scaling numbers, but you'll get different prefactors in front of that expression. But it's sort of useful nonetheless because of it's this weak function, which ultimately derives from the fact that the dipole field strength is falling off very, very rapidly with distance from the star. So however you do this estimate, all the uncertainties sort of get swept into that very rapid fall-off, and you get reasonably similar numbers for your prediction for where the magnetosphere is. And what you find then is that if the star has a kilogauss magnetic field, which is maybe not unreasonable, for an accretion rate of about 10 to the minus 8 solar masses per year, this magnetospheric radius is typically 10 or 20 solar radii, so it's maybe 5 to 10 stellar radii for one of these young stars that is somewhat larger than the Sun. So this has various qualitative consequences for the nature of accretion in these systems. It implies that the gas accretes along stellar magnetic field lines. Effectively, it reaches the stellar surface almost in free fall, and therefore forms an accretion shock on the stellar surface. And then, moreover, the magnetic field allows, in principle, there to be a sharing of angular momentum between the rotating star and the disk. In principle, a rapidly rotating star could spin down by transporting some of its angular momentum magnetically to the disk, where it would then flow outwards through the disk due to the usual viscous evolution of the disk. And of course, most obviously, it means that the innermost disk is missing. The innermost part of the flow is this magnetospheric flow, rather than having a disk which extends all the way to the stellar surface. Moreover, when people do simulations of this is work by Dider et al., what they tend to find is that the region where the disk is being truncated by the magnetosphere is rather a good location for launching high-velocity outflows from the system. So if one's interested in understanding where jets come from in young stars, this may be pinned to the location where this disk is interacting strongly with the stellar magnetosphere and actually throwing out material along magnetic field lines that perhaps is eventually being collimated into the jets we see in some young stellar systems. Okay, so that's one case where in principle we can go away from having a zero torque boundary condition at the inner edge and instead have a non-zero torque at that location. Another case where this can happen is if we have a disk which is surrounding a pair of stars in a binary, a so-called circumbinary disk. And here the idea is that the gravitational torques from this rotating binary can in principle completely prohibit accretion taking place through some exterior radius to the binary, which would define the inner edge of the circumbinary disk. So in one-dimensional viscous models, where we're considering the evolution of the disk, the condition would be that the radial velocity is 0. This would be the expression for the radial velocity. The radial velocity is 0 at some radius r equals Rn. And this situation also has an analytic solution for how the disk would behave. And now it's not really an accretion disk, but so much of a decretion disk, because now by construction, we're not allowing any material to flow in and join either of the two stars in the binary. So in this case, the disk angular momentum increases due to the binary torque, which is preventing the material accreting onto the star, and therefore both the mass and the angular momentum in the disk eventually flow outwards. Meanwhile, of course, that energy and angular momentum has to come from somewhere, and so the binary would have to shrink and give up energy and angular momentum to the disk in order for angular momentum to be conserved for the entire system. So there's, as I mentioned, an analytic solution to this due to Pringle from 1991. So here we have, again, a ring of material placed around the binary now, and now as the system evolves, initially the material moves inwards to encounter this brick wall, basically, that's being imposed by the binary, but then as time goes on, the mass is conserved in the disk, and the disk just expands outwards with extra time. So this is what you might get in a binary system. It's also interesting because this is, if you like, the prototype for what's called type 2 migration of planets, where we have a very unequal mass binary, but where the physics of how the interaction takes place with the disk has some similarities. However, when we look at this even in binary systems, we see that this kind of analytic approximation for how the dynamics works is not actually that good. So I'm going to show a movie here, and what we have here is a binary interacting actually with a massive disk, which is self-gravitating. So we're looking in a co-rotating frame here. Here's the binary. Here's the disk. We'll just let that play. And the key point to notice here is that, as you can see, you do have this cavity around the binary, which is established by this gravitational torque. But as you can see, at all times, some of the gas is making it sort of through this barrier and is actually temporarily forming little accretion disks around the two stars. So in practice, even though the binary does exert a torque on the disk and export some of its angular momentum to the disk and shrink in response, there's also mass accretion which makes it past that barrier and gets accreted, in this case, by the individual components of the binary. And as I think we might hear later in the week, this kind of mass flow across this angular momentum barrier turns out to be rather important for understanding both massive planet growth and also how rapidly planets would migrate inwards through protoplanetary disks. So this is important physics, and a critical issue that remains somewhat open is really how this operates with realistic models for disk turbulence. So this particular calculation I was showing here was for a self-gravitating disk, which might apply to a young binary surrounded by a very massive disk. But if instead we're interested in planetary migration, we might instead be worrying about magnetohydrodynamic processes taking place within the disk, and how those exactly cause gas to flow across these barriers is not so well worked out. So we'll say a little bit about winds tomorrow and then discuss some turbulence, but I think we should stop here for today. Yeah, so I would say, so the question was, are there measurements of alpha? And I would say measurements that, or inferences that are made from disk evolution, so from statistics of disks and from change of accretion rate with time, those tend to come out with numbers that are of the order of this 0.01, okay, which is sort of as it should be. There's then a separate class of measurements you could make, which would be to look, say, at dust settling. And those measurements, interpreted again in the most straightforward way, tend to give much lower numbers. So T-Tauri disks, for example, the disks are probably not as flared as you would expect if material was suspended with an alpha of 0.01, and the sort of naive number people get there is more like 10 to the minus 4. So maybe that says, indeed, that alpha is not a good, or is not a single parameter description of those two different physical processes.
Leonardo may also come up with some ways to measure constraints on alpha.
Just a question about the animation you showed on the last slide. It seemed to show that binary orbit was changing slightly due to this accretion. Is there anything interesting about the kind of statistical parameters of the binary orbits that comes from this at all, or is the parameter space just too narrow in that set of simulation?
Yeah, so what was happening there was that this kind of interaction can excite eccentricity in the binary. In fact, that was the reason these simulations were being done. And so I think if you imagine this kind of process takes place in binary stars, then it is a way perhaps to go from circular binaries to binaries maybe with eccentricities of 0.3 or 0.4. How well that carries over to the planetary case involves some extra things, and it's probably much harder to excite eccentricity if you do this for a very unequal mass ratio, such as you'd have in a planetary system.
And please remember to say the question in case they can't tell from your answer.
The physical explanation of the viscosity is always related to the magnetic field.
Yeah, so the question was, is the physical origin of the viscosity generally related to the magnetic fields? I would say in almost all accreting systems, the answer is very likely yes. The viscosity is due to magnetic turbulence. In protoplanetary disks, it's not clear. Certainly, we can take the magnetic mechanisms that work in other disks and apply them to protoplanetary disks, and they will generally give some amount of angular momentum transport. But it may be that other processes, which we'll talk about tomorrow, which are more related to thermal effects in the disk, entropy in the disk, may also play a role, and we really don't know.
It's great to have so many questions. I'm going to take one more, though, and then I think we need to move to our next speaker.
For the disk with strong magnetic field, you said the innermost part of the disk, they vanish. Is it because of the strong toroidal fields you have, generally, which are also responsible for jets and something? I've seen this in black holes and those kinds of accretion. Is it the reason behind that?
Okay, yeah, so the question is the reason for the innermost disk being missing around a magnetized object. And yes, indeed, it's due to the pressure, ultimately, of the magnetic field. So in the very simplest analysis, you could just consider the pressure of the magnetic field and compare that with the Ram pressure of the inflowing material. And that would give you basically the same expression I gave for where the magnetosphere takes place. And we think similar things happen around white dwarfs and around neutron stars if those are sufficiently magnetized. Around black holes, the inner disk is missing due to the fact that just the orbits are unstable, sufficiently close in the relativistic potential. But yes, in basically all magnetized objects would have similar dynamics and would potentially produce outflows as well. Yes.